Hello, everybody, and welcome. We are so glad that you are here for today's sponsored webinar, Nitrogen Rejection via Membrane Technology. Before we get started, I'd like to take just a minute to go over a few housekeeping items to help you get the most out of today's session. First, your microphone and camera are off by default, so there's no need to worry about background noise. If you'd like to share a comment or chat with other attendees, you can use the chat feature located in the toolbar at the bottom of your screen. Just be sure whether to select you'd like to communicate with everyone on the webinar or with the hosts and panelists directly. If you have a question for our speaker, please use the Q&A box also in that bottom toolbar. You can type your question at any time during the webinar, and you'll also have the opportunity to submit your question anonymously and upvote others' questions that you're interested in hearing answered. This session is being recorded, and a link to the recording will be sent to all registrants by the end of the week. If you're experiencing any technical difficulties or audio issues, try adjusting your Zoom settings. You can also send us a message using the chat, and we'll do our best to help. Thank you to our speaker, Gregory Myrick, and to Air Liquide for sponsoring this webinar. Their sponsorship directly supports the American Biogas Council and our programs. And finally, thank you all for joining us today. Now, I'll hand it off to our moderator, Jonathan, and our speaker, Greg, to lead you through the great presentation we have for you today. John and Greg, please take it away.
Good afternoon, everyone. Thanks so much for participating in today's webinar. Today, we're pleased to be joined by Greg Myrick, Technical Director for Advanced Separations at Air Liquide. Greg is a chemical engineer with over a decade of experience in the industrial gas sector. In his current role, he serves as Technical Director for Global Markets and Technologies at Air Liquide and is a member of the company's international technical community, where he focuses on innovation and development in industrial gas and bulk material production processes. He has played a key role in advancing membrane technology across the biogas, natural gas, and nitrogen sectors. Greg is a recognized innovator with 3 patents filed for membrane gas separation processes. In 2023, he was honored as an Air Liquide innovator for his work on a small biogas upgrading skid deployed on a digester in Brazil. His achievements also include being part of the design team for Air Liquide's membrane nitrogen removal technology, which received the American Biogas Council's Biogas Innovation of the Year award in 2019. Over the course of his career, Greg has designed, executed, and commissioned more than 20 full biogas projects and contributed in part to over 100 others utilizing Air Liquide's upgrading equipment. With that, I will turn it over to Greg to begin his presentation.
Thank you so much, John. Really appreciate it. I really appreciate ABC letting us give this presentation today, and hopefully you all learned something from it. And if not, we're happy to discuss the individual topic that you may have. So thanks again, John. Thanks, Erica, and thanks to the ABC. So today, here's what we're going to discuss at Air Liquide. Safety is our #1 priority, so we always like to start off our presentations with a safety moment, and I feel like this is no different. So I'd like to start off with a safety moment. Then I want to answer some of these questions for you. Who are we at Air Liquide? What problem are you facing? Nitrogen out of the landfill. How do membranes work? And then how can they help potentially solve this problem for you? And then give you a little bit of when and where we've implemented this technology. And then we'll keep the Q&A till the end. So excited to answer some of your questions, any and all of your questions. Go ahead, next slide. Next slide. So for safety in a landfill, flammability and a fire is really our main challenge. So you need 3 main things to start a fire. You need a fuel source, landfill methane. You need a heat source, a thermal oxidizer or a candlestick flare that's typically on site. And then you need oxygen. Oxygen comes from pulling vacuum on the well field and that air intrusion. So with the nitrogen that you're building, the oxygen is coming with it. And with that becomes a very serious safety risk. So typically biogas upgrading technologies concentrate methane by removing CO2 and oxygen. In that concentrated CO2 and oxygen stream, you have the potential to create a very serious situation. So the dark blue dot on the right side is a typical landfill feed gas composition. that blue line that's running through the triangle, the flammability triangle there, is going to be air in the presence of methane. And the bottom of that is pure air. So 79% nitrogen, 21% oxygen. So when you have air intrusion, you're taking that dark blue line and you're dragging it down to the bottom. And so when you see that dotted line go through the dark orange triangle, you are in a potentially flammable environment, which is really dangerous, because once you're in that flammable environment, all you need is an ignition source. So adding safeguards to your processes will help you stay out of that flammability mixture. The main number to think about is this LOC, limiting oxygen concentration, of 12%. So if you're able to maintain an oxygen level less than 12%, which again, the concern is not necessarily in the feed gas, which you're not going to have 12% out of your landfill, but in the concentrated CO2 oxygen stream, you may get to that level. So that is the concern to stay away from and to think about when you're designing these facilities. Next slide. So a little bit about Air Liquide and why we're in the biogas space and how are we contributing to the environment. Next slide, please. So at Air Liquide, we have a division called Advanced Separations. This is a membrane manufacturing and membrane solution development for the industry, both in biogas, natural gas, helium, hydrogen, and nitrogen mainly. We manufacture a hollow fiber membrane where it's effectively the size of a human hair, but has a hole down the middle of the human hair. I have an example here of one of our membranes, a little bit exploded, but fun to look at nonetheless. So at Advanced Separations, we develop our own fibers, new formulas, and develop membrane modules, as well as apply them to new technologies and new applications wherever we can. Our research and development is here in Delaware, where I am sitting right now. We have over 37 years of membrane production experience. Everything we manufacture that gets sent globally is manufactured here in the US. And we have over 10,000 purification units in those areas that I mentioned before of helium, hydrogen, biogas, nitrogen, and natural gas. Next slide, please. At Air Liquide, we're really focused on driving innovations. Jonathan very graciously mentioned some of the innovations that I've been involved in, but Air Liquide is very keen on how can we drive innovation in the market. So our membranes are on land in a landfill, in the air, potentially on an airplane that you've ridden on recently, and then in the sea in a FPSO, which is floating platform storage and offloading for natural gas. Here are a couple of the achievements that we have had in the last couple of years associated with those different, in addition to using AI in our manufacturing process, developing new membranes, and then really our standardization initiatives, which you'll hear more about in the coming months, and really rolled out fully next year. So in natural gas, we are focused on recovery of natural gas from oil refineries, hydrogen, huge improvements on recovery as well. Nitrogen and helium, we're focused on lowering the cost of recovering both of those. And then the discussion that we'll have today on nitrogen removal for biogas, and a lot of really exciting innovations that will be coming out the end of this year as well as next year in the biogas space that we're really excited about. Next slide, please. So at Air Liquide, we are involved in the whole circular innovation strategy. So research and investigation, again, here in our Delaware Research and Development facility, where we're developing new polymers. That then goes to our production facility in Newport, Delaware, where we are focused on lead time and ensuring the product quality for our customers. We have an in-house engineering and design team, so we develop and design the skids ourselves and work on providing the best performance that we can for our customers. Then finally, we bring that into the field with our field service organization that is reliant on providing the customer the best membrane support that we can, tuning those membranes when they're running, and then optimizing the gas production. What's really fun and unique about this strategy is we can then use the engineering and design and the field service to then feed back, where can we improve in polymers? Where can we improve in our engineered design? How can we provide the best value to the customer? So having that circular loop really helps us provide the best end result for our customers. Next slide, please. So at Air Liquide, we have over 250 worldwide references in biogas. Here are our references in North America, and we have been doing this for the past 20 years. So all of these dots are sites where Air Liquide equipment is in the biogas space. So we have our yellow, which is the operating facilities. We have green, which there are 8 facilities that are running with nitrogen removal technology. Finally, there's blue in sites that are in development. Some of those projects have already started up. And then we have our purple and red, which are our manufacturing as well as our corporate office throughout. So spanning across the US, I've been fortunate enough to be at a lot of those sites and try to help out and tune the systems as much as possible, and continue to grow this portfolio of projects, and hopefully a few more of those green dots as we continue to grow this technology in particular. Next slide, please. So what is the problem that we're facing in the biogas space? And it's really a nitrogen problem. Separating methane from CO2 is relatively easy. There's a lot of technologies that can do that. Separating methane from nitrogen is very difficult. And so one of the biggest concern and the largest CapEx and OpEx involvement in these projects is typically in nitrogen removal. Next slide, please. So where is the nitrogen coming from? It's really a landfill problem more than it is a digester problem. So in a digester, you have better control over the nitrogen. In a landfill, it's a function of pulling vacuum on the wellhead. So there's a little picture from the EPA of a wellhead, and the example is, okay, the cap that the wellhead that's protruding the cap is pulling vacuum on the tube that's going down into the waste and drawing in the methane from the waste. So when it does that, if you pull too hard, it's also going to bring air from the atmosphere through the cap into that collection well. And so that's really where the problem comes, as well as if you have an open landfill, you have the open face additionally bringing in some nitrogen. So when we talk about the different ranges of nitrogen that could be coming from a landfill, you have these 4 categories. You have the understressed or a closed landfill, so where there's not a huge risk of additional nitrogen intrusion. And understressed means you have an appropriate well field management and not too much vacuum being pulled. So just enough to draw out the methane from the waste, but not so much that you're bringing in the air intrusion from the atmosphere. A typical normal range is going to be more your 6 to 12%, though. That'll be appropriate emission mitigation, as well as the maximum gas collection that you can. Once you start to get into the 16 to 20 and over 20%, you're really dealing in residential areas where you have to be really worried about emissions for the neighboring town, or if you have specific EPA concerns of mitigating that that gas from getting out. When I've seen over 20%, that's a developer that just wants to get as much gas as possible, right? So they think, oh, I'm going to over pull in the well field to get as much gas as possible. But if at the end of the day, you're having to remove that anyway, you're just adding CapEx and OpEx that isn't helping you along the way. So there is a pivot point. And interestingly enough, back in 2011, Jeff Pierce with SES gave a presentation at LMOP where he said it's more cost effective to minimize nitrogen entry into the well field than it is to remove nitrogen in the upgrading plant. And it was true back in 2011. It's true today. It's so much more cost effective to be able to get rid of this before it ever becomes a problem. So if we can continue to advocate on, hey, let's treat it on the well field, then you're really saving your project capital significantly in developing these projects. And it becomes more and more prevalent as you try to get to lower and lower landfill flow rates, where the CapEx of adding additional equipment start to become cost prohibitive to operating these projects. So I did a little bit of a comparison here using our technology to show what that comparison is. So 6% nitrogen was kind of the base case that we would design this project to. If we were to get 4%, somebody did a good job managing the well field and had 4% on the feed, we got better recovery of the methane as well as lower compression costs. Conversely, if it was run at higher than designed nitrogen levels, you would have too much recycle and you would have a big impact on methane recovery. And that's relevant across all the technologies, but just wanted to kind of give you that scale of it's really cost prohibitive to have high nitrogen coming out of the well field. So let's get into what are the commercially available technologies. Next slide, please. Next slide. So here are generally the commercially available technologies. We're broken into three categories here. We have PSA, membranes, and cryogenics. There are other technologies which touch on in the next slide, but these are going to be the major players in the market right now. So kinetic PSA is going to be your lowest cost option here, but you pay for it with lower recovery. In a kinetic PSA, you are letting the methane pass through and the media is grabbing hold of the nitrogen. So that's why it's able to stay at high pressure, the product gas at high pressure. Then conversely, the equilibrium PSA is going to hold on to the methane and release the nitrogen at high pressure. So then you need additional equipment of a vacuum pump to draw the methane out of the media. So you're adding additional costs of compression to achieve that higher recovery. For a membrane, similarly, rather than pulling vacuum on the low pressure side, we need to boost the pressure prior to the treatment, and that helps with CapEx considerations and keeping the footprint nice and small. So while it's similar in relation to the equilibrium PSA from a compression standpoint, the footprint is really the added benefit there. And then cryogenic is really going to be for your high flows, high nitrogen, something that justifies the cost of all that additional equipment. Still high recovery like the other two technologies, similar low pressure. So in all of those high recovery options, you're having to boost up the product pressure to your pipeline pressure anyway. It's just a matter of how do you want to get there. And then some of the challenges with the equilibrium PSA and the cryogenics are going to be related to compressor oil or impurities from the landfill, such as VOCs. All of those can negatively impact the PSA technology or cryogenic technology by, in the PSA, it's going to reduce your adsorptive capacity by clogging the pores. And then in cryogenics, it's got a much lower freezing point and so could freeze up within the cryogenic equipment. So the intent here of this slide is to give you guys a high level, how are these technologies comparing from one to another, and give you a sense that no technology is going to be broadly applicable to every use, and you need to evaluate your feed conditions and your plant economics that make sense for these different technologies. So they all have their benefits, all have their drawbacks, and it's what's the right case for you. Next slide, please. So a little bit of a check-in, a question. You can see my AI-generated friend here of nitrogen brings me a lot of joy because he's got 3 arms, which makes no sense, but AI historically hasn't done a good job of drawing hands, so this is no different. So as you'll see in the poll, and we're excited to hear what you have here. So you could either have good wellfield management, which is good on you. That's fantastic. Do you have PSA adsorption technologies, cryogenic, membrane? The solution to pollution is dilution approach of just diluting the end product. Biological, which is typically going to be in your wastewater space, so wastewater treatment plants. And then others, there's something that I haven't listed here that I'd be excited to hear what you got. Or are you doing none of this and this is really a fact-finding approach? So give you a moment. I guess we can close the poll and see where we're at, Erica. Okay, so a lot of PSA, nearly 40% PSA, 10% wellfield management. Again, great. Love to see that. Nice to see some membrane in there, and then none. Which is good if you don't need it. That's even better. If you don't have it and do need it, then it's exciting to see the different options. So a lot of PSA and in general, very good technology. But again, comes up to that impact of impurities and how to best manage that. So great. Next slide, please. All right, so a little bit of background on membranes. We're going to touch on what is a hollow fiber and how does it work, and then specifically nitrogen removal membranes. So next slide, please. Got a nice little video for you. So this video is specific to nitrogen solutions, but it is applicable to how a hollow fiber works. So we have this center tube, which adds structural stability, and then we wrap the membranes or the hollow fibers around that center tube. As I mentioned before, each one is the size of a human hair, and very small. Here we have O-rings that are keeping the high pressure side from the low pressure side. So the high pressure is going to go down the bore of the fiber, and then it will permeate across the membrane wall that's at low pressure. This is an example of our 12-inch housing that in some applications we can have up to 24 bar pressure. In biogas, you don't typically run that way. And then it's zinc chromate plated to improve corrosion resistance. So as we take a snapshot into a fiber, you can kind of see the gas is going down the bore, and then our fast gas, the example of a fast gas here, is going to pass through the membrane wall, and our slow gas is going to stay along the fiber. So I said this was air service, so the air is going to be our landfill gas. Nitrogen is going to be our methane gas in biogas service, and then O2 is going to be CO2 and oxygen that permeates across the wall. But just to give you a flow dynamic perspective. So the membranes are easy to replace how we've designed them. We have installations that have nearly 20 years of run life with the original membranes. Typically, we say 10-year membrane life, assuming proper pretreatment and protection of the membrane. We also have a 6-inch variation here. And so, wanted to highlight that with the proper pretreatment, you can keep these membranes for quite a long time. The 20-year reference is an Air Liquide owned and operated site that we've had since 2007, nearly 20 years. Next slide, please. So how this differs slightly from our nitrogen removal membranes. Our nitrogen removal membranes are a polyether-ether ketone substrate. This allows us really great thermomechanical properties as well as chemical resistance so that it can sustain oil contamination, VOC contamination with no loss in performance. It allows the membrane to then operate with very little pretreatment and keeps that overall cost down. This was an acquisition that we had back in 2016, and we use a proprietary coating process that has best-in-class methane nitrogen selectivity. So really reduces the overall power consumption by having that improved selectivity. The example of the polymer is here. The picture in the middle is a hot wire cut where we're cutting off the end of the fiber to expose the fibers and allow for that permeation across. And then an example of a bundle is there in the bottom right. And so with that, touching back on the chemical resistance, we've had examples where we have flooded, the process has been flooded with oil. We've taken the membranes out, cleaned them, put them back into service with the exact same performance that they had on day one. So they are very resistant to these chemical attacks and VOCs. And that really helps at the end of the day in keeping your overall cost down. Next slide, please. So here we have a kind of how does this differ from a conventional technology, conventional CO2 removal technology versus this PeakSet product. So I was mentioning during the video that the fast gas is what's going to pass across the membrane wall, and then your slow gas is what's going to stay through. So in a conventional CO2, that there are many players in the market in this space, those membranes can't differentiate between methane and nitrogen. They're chemically too similar for a CO2 removal membrane. And so really we're counting on the fact that we can keep the methane at high pressure, and then the CO2 is going to very quickly pass across the membrane wall. The difference with the PeakSet products is that we can drive a wedge between the methane and the nitrogen. So we're flipping it on its head. It's keeping the nitrogen at high pressure, we've swapped it such that the methane is now at low pressure, and we're really driving a wedge between methane and nitrogen. A good point here is that oxygen is not shown on the graph. It will behave similarly to CO2 with these membranes. So it will permeate across with the membrane, with the methane, excuse me. And in doing that, as you remove nitrogen, it will slightly concentrate, but not significantly. So it'll pass with the methane. Next slide, please. Okay, so this poll is really a question of, did you pay attention? So through this presentation, this question has already been answered. So I'm excited to see how many of you are paying attention. How many fibers can we find in a 12-inch diameter bundle? So think about 12-inch in diameter. Do we have 5 fibers in there? Do we have 500 fibers, 1,000, 10,000, 100,000, a million, or 10 million fibers within a 12-inch bundle? So again, we're thinking, make sure my video. So this is a 2-inch diameter membrane with the end cut off and individual hairs. It kind of feels like a big pom-pom. Very fun to play with. Nice little fidget. Okay. Let's see where we're at. How many guesses? How many people have been paying attention? Majority of you. Majority, but not more than 50%. So 47%, it is a million fibers. It's about 1.2 million. 10 billion would be, or 10 million would be really big. 100,000 is actually a very good guess because depending on the fiber diameter may change, and also depending on, whether it's an 8-inch or a 6-inch bundle may also change. So depending on the product line, where we have 6-inch membranes, 8-inch membranes, 12-inch membranes, we have a variety of options for the application. Could be between 100,000 and a million. All right, but majority rules and majority have been paying attention, so I appreciate that. All right, now let's get into why you're all here, the nitrogen rejection unit that we have at Air Liquide. Next slide, please. So we have a patented process at Air Liquide. It's the patent listed there and shown in the diagram below, where we are taking our landfill gas, processing it through a CO2 removal step. I like Air Liquide's CO2 removal step, but it could be any CO2 removal step at that point. You are concentrating up the nitrogen by removal of CO2, then compressing it up before going into the membrane stages. Again, we're compressing it to reduce our overall capital as well as the footprint. So keeping the footprint nice and small, which works well for small landfills and landfills in general where you're space limited. Goes through a 3-step membrane process. It leaves the high pressure to be your nitrogen, and the nitrogen is 70% give or take content wise, and it's a very low flow. So typically we see this used as a fuel gas or a supplemental fuel gas for your thermal oxidizer. And then on the low pressure side, you have pipeline quality gas of less than 3% nitrogen. And that then gets compressed up into the pipeline. So on the front end, your compression is typically going to be a single stage compressor. We're starting at, say, 200 pounds as you go through the CO2 removal step, and then 200 pounds to 500 pounds can be achieved in a single stage, which is why that number was chosen. Nice small membrane skid, and then multi-stage for compression. But that wasn't good enough for us. So we then went and tried to continue to innovate. Next slide, please. So we have a second patent associated with our nitrogen removal, which is our cold nitrogen removal process. And really, this is a great slide to give you a sense of what the difference is and the capabilities, some of the capabilities to let you really think about how this could apply for you. So very similar process scheme to what was shown before. And the difference is we're using a multi-stream cross exchanger to achieve subambient temperatures, minus 20 F feed temperatures, for example. No additional chilling is required, right? In the cryogenic case, you have additional liquid nitrogen at times, not all the time, but at times you have additional source of liquid nitrogen. Here, no additional equipment's necessary, not an additional chiller or anything like that. We can all do that within the membrane skid itself. So we're using that process improvement to really get the most out of the equipment that we can. So show the example of the generation 1, the previous slide that was shown. Are a generally typical scheme of 6% nitrogen on the well field, 10% nitrogen coming into the nitrogen skid, 3% product composition, which then correlates with a 4% total inert pipeline spec is very common to achieve 96% recovery. And then the recycle ratio here I have is I'm listing as comparable to PSA of a similar size, right? So the PSA manufacturers aren't going to say this recycle ratio. They're going to say with the vacuum pumps, you have X compression. So this pairs very similarly to that compression requirement associated with the vacuum pumps at those conditions. So then the improvement, we can tailor it to whatever your needs are. Do you need less compression? We have all the same conditions with a lower compression ratio. Hey, is my pipeline spec tighter? Do I need a lower nitrogen coming in? We could achieve that at the same conditions that we could before, but with a lower nitrogen composition on the outlet. Or you have a lot of nitrogen coming from the feed, we can now take twice as much nitrogen than as we were able to do before, from 6% to 12% at the exact same process conditions of 96% and the recycle ratio listed. So let your mind explore the options there and how could that maybe improve and upgrade your nitrogen removal solution that you may have today or are looking for in the future. Additionally, right, I listed all these at 96%. There's also a run where we can achieve higher than 96% recycle, higher than 96% methane recovery on the nitrogen removal system, and achieve the 3% at 6% nitrogen. So really, we're looking to open the conversation on what do you need and how can we best serve you with this solution. Next slide, please. So some of the advantages are footprint, right? I listed this before of 80% less than the standard PSA, modular skid design, really improves the space efficiency. It's a single point of integration, which really reduces your skid costs. The picture shown here is 1500 SCFM. But as you can see, there's some expansion capability. The skid could likely process 3000 SCFM worth of nitrogen. And this was a 5% to 8% nitrogen case. Really wide operating range from a flow perspective, from a composition perspective, has the expansion capability, but then can also turn down. So this could turn down to 25% of its feed capacity, which is a big driver for a lot of our customers today. And then I've already mentioned the contaminant resistance, but this is the skid that you would get, and you don't need any additional equipment to protect that. Next slide, please. So a couple of case studies that we have wrapping up here. So the first case study, next slide, please, is Air Liquide owned and operated Glacier Ridge landfill in Horicon, Wisconsin. 2600 SCFM, that's the skid that you see right there. It's been in operation since 2020 and has a total plant uptime of 98%. So that's total plant, not just specific to the nitrogen removal, which would then be higher than 98% for just that piece of equipment. In this example, we have 8% nitrogen in the feed, which gets 13% nitrogen to the NRU. It has greater than 96% purity, product purity, as we are injecting into a 4% inert product pipeline, and then consistently 96% or high and higher methane recovery at this facility. Next slide, please. We have 8, I mentioned at the beginning, we have 8 total references in the biogas space, and we have 1 in the natural gas space, which is the upper left, which is utilizing the cold NRU concept and has been operating since October of 2020. Our first reference was in Arlington, Texas, so the technology has been in operation since 2019. It was the ABC Innovation of the Year in 2019 as well. I'm very thankful to the ABC for recognizing this achievement. And one of the other really fascinating things about the Arlington facility in particular is that it is a mixed feed. So it's coming from multiple landfills as well as a digester source. So they're able to tune in the nitrogen to what they need. It's processing 4,000 SCFM, but scalable to 5,100 SCFM. It's got 6% nitrogen in the feed and 10% nitrogen to the NRU. Because it's generation 1, it had slightly lower recovery, but since then we've been improving the recovery due to process improvements as well as membrane improvements that we've been making since that was in operation. So we're really excited about where this technology is going, and particularly how the cold NRU concept could take this and your project to the next level. So we're happy to discuss this with you, and yeah, ready to open the floor to questions. Next slide.
All right, thanks, Greg. Great presentation. Definitely got quite a few questions during that. So I'll start going down the list here. All right. So the hollow fiber membrane manufacturing process looks quite tricky. How much more expensive are hollow fiber membranes compared to other alternatives like rolled sheet membranes?
So from a ability to process standpoint, the hollow fiber membrane is significantly more efficient than processing using using flat sheet. So with flat sheet, you need a lot more surface area to process the same amount of gas flow. So in our experience, the flat sheet has not been cost effective in this space because of the amount of area that you would need, particularly related to nitrogen removal.
All right, next question. If PSA and cryogenic can remove CO2, O2, and nitrogen while membranes can't, why would someone want to choose Air Liquide's membranes when all those are in the gas?
Sure. So it's a great point. The CO2 in particular, regardless of the technology, not one technology can remove CO2 and nitrogen together within one process unit. So there are PSAs that remove CO2 and there are PSAs that remove nitrogen, but there's not a single PSA that removes both CO2 and nitrogen together. So you have 2 unit ops in that case. In the cryogenic case, you still need to remove the CO2 prior to the cryogenics. So you have a PSA to remove CO2 in that example as well. So then we're talking about oxygen and nitrogen. The other technologies do remove oxygen to a degree. In cryogenics, you are limited by the amount of oxygen, and that is ultimately your driving force in recovery. For membranes, we feel like the simplicity that the membrane offers then pairs nicely with a technology like a deoxo, in the sense that some pipeline specifications require a deoxo regardless of the technology. And so then this technology is simpler to operate in conjunction with deoxo.
Next questions. Do your membranes contain forever chemicals? How do you dispose of the spent membranes after use?
So they do not contain PFAS or forever chemicals. They do contain silicon, proprietary silicon material. So there's no harm to disposing of these in a landfill. It's not going to help with your gas generation, but there's no harm in disposing of these in a landfill. Again, like touching it, no adverse effects. They're okay to touch. We had a situation where we had it come back from a landfill after being inerted, and our processing team was very worried about it. I was like, nope, we're all good. As soon as you inert with nitrogen, there's nothing left, no adverse effects. So it's okay.
Next question. It seems methane is the permeate of the membrane. At what pressure do you get the methane out of the system or out from the system?
Yeah, so it'll be positive pressure, typically within the 15 to 50 psi range. It's kind of a function of the product compressor and what the suction of the product compressor is running at. So we have a control valve, and then we have the product compression. So both of those are dictating what the pressure that the membrane sees is. But in between that 15 to 50 range is a good takeoff pressure before the product compression.
Next question. How do you sorry. How do you process respond when the pipeline quality required is 98% methane?
Yeah, so it's a tighter spec. And I think the key there is finding a technology that works for your specific requirements, right? If it's a really tight oxygen spec, for example, if it's a really tight nitrogen spec, that may drive you outside of the project economics, that makes sense to be able to process that level of gas. So if it's higher than 98%, then we would look at what is the feed gas coming in. What are some knobs to turn, right? If we can remove additional CO2 to be able to get that 98%, we'll look at that knob as well. And then managing the nitrogen level to stay below that. But we have product gas analyzers to ensure that our pipeline quality always stays below whatever the design threshold is. So we'll design to that value, long story short.
I had a couple questions on this. I was trying to find the exact language, but someone just put one in the chat too that was similar, so I'll read from there. What kind of pretreatment is required to protect the membranes? What are the more critical contaminants to consider for the nitrogen membranes?
So for the nitrogen membranes, different than the CO2 membranes. So most CO2 membranes are going to be easily impacted by VOCs, such as vinyl chloride, xylenes, acetones, all of those VOCs that are very prevalent in landfill gas. And so for CO2 applications, you need to have really tight pretreatment to be to protect those membranes. The nitrogen membranes are not impacted by those same VOCs. Granted, they have been through that process, right? They've been through treatment, so you still have, say, 10 ppm worth of those VOCs that would never negatively impact the CO2 membrane, does not impact the nitrogen membrane at all. And as I mentioned, the nitrogen membrane, we have reference cases of flooding it with oil, multiple reference cases of flooding it with oil, unfortunately. And then with proper cleaning, put it back into service and had the exact same performance as it did day one. So it really does not need any additional pretreatment. Liquid water on the inlet, not a big fan of. You're plugging up pores and all that. But aside from that, it also doesn't like liquid oil, but just means you have additional processing steps to clean that out before putting it back in service.
Regarding scale, what is the range of flow rates that Air Liquide's NTU is designed for? Is there a unit designed for for as low as 500 SCFM at the lower end?
Yeah, absolutely. So as I mentioned, the feed pressure is a function of CapEx. So if we lower that feed pressure, it gives us more flexibility to process lower feed gas condition, lower flow feed gas conditions. So we can absolutely process 500 SCFM on the coming off of the well field and scale up to as big a project as you have. It really just boils down to what is the nitrogen content that drives the economics of that individual project. But in the case in one of the case studies of the 1500 SCFM, we could turn down to 25% in that example. So what is that, 300 SCFM? So we could absolutely process at 500 SCFM. Oh, and lower, kind of as needed.
Is Air Liquide capable of integrating an entire system to take raw landfill gas all the way to RNG?
We have done that in the past, and are capable of doing that with the engineering resources that we have in-house. It becomes a question of expertise. There are people that do this 24/7, but one of the projects that I worked on, we supplied from, in this case, it was a digester, the gas off of the digester, compression, pretreatment, membrane skid, product compression. Didn't supply the interconnect, but nobody does. So we took all of that in-house. So we're very capable of doing that, but would need to find the right situation for the individual. And happy to have that discussion.
And Greg, forgive me, I don't think I'm being duplicative on this question. There may have been a similar question, but let me know if this is too duplicative. Can an Air Liquide membrane handle impurities, or does it need to have pretreatments before the membranes?
Yeah, so a little bit the similar question to before, but really no pretreatment necessary other than, particulate filter. Again, we're talking very small holes, so if you plug one with some dust, it's not going to be able to process that gas. But these membranes in particular, with very little pretreatment, that is not costly at all, right? Other technologies, you need large carbon vessels, a lot of dehydration and chilling. These don't need that ahead of time. We need a slight dew point so that we're not getting liquid water, slight dew point margin so that we're not getting liquid water, and then particulate filter to make sure that we're not getting any additional dust in there.
And on this one, I'm not sure if the attendee was saying that they're using membrane to achieve 96% methane recovery, but I'll just kind of read it as is. Using membrane to achieve 96% methane recovery, what is the nitrogen slash methane selectivity needed?
Yeah, sure. So I'm not going to get into the exact selectivity just for proprietary reasons, but it's not necessarily a question of selectivity to achieve those recoveries. It's a question of recycle rates. So the higher the selectivity, the lower the recycle rate required. So the less amount going around required. But to achieve that level of recovery, it's just a function of how many times are you sending this gas back through process. So higher and higher higher and higher selectivities will get you lower and lower recoveries, which all of our innovations are pushing towards that high selectivity to get the maximum out of these processes.
What's your upper limit of nitrogen removal capacity in percentage of incoming flow?
Percentage of incoming. Yeah. So we have design systems at 16% feed nitrogen, where we feel like the economics make sense. As you get north of that 16%, it may not work as well from an economic standpoint. It's going to work from a processing standpoint, but the economics may not drive you to make that decision to go towards membranes. But at 16%, we feel very confident in the solution that we have.
Does the map of Air Liquide's NRUs show membrane-based NRUs, or are all NRUs regardless of technology type?
Those are just Air Liquide membrane-based NRUs. Yeah. So there were 8 references in that map.
Would you comment on the impact of VOCs on membrane technology?
Yeah, so VOCs in general on CO2 membranes are very negatively impacting the process, but that's no different to a PSA or cryogenics. All 3 of those technologies need VOCs to be removed prior to the processing capability. In the unlikely event that you would have this nitrogen removal upstream, and I say unlikely because you then still have to process that CO2, but if you had nitrogen as your first step, these nitrogen removal membranes would not require any additional pretreatment for the VOCs. But economically, it doesn't make sense because you still have to remove the CO2 at that point. So you're more resistant, your less resistant membrane needs to go first to remove the CO2 to then have your more robust membrane remove the nitrogen. We looked heavily into that process scheme and what winds up being the lowest cost option. And unfortunately, it's CO2 removal, then nitrogen removal.
Can you please explain why the percentage of nitrogen to the NRU is higher than that in the feed, please?
Yeah, absolutely. So when you are removing CO2, your mole percent increases the other components. So if you have 50% methane and 10% nitrogen and 40% CO2, you're getting rid of all that 40% CO2 while methane and nitrogen are still there. So methane concentrates up to 90% or 85%, and then nitrogen still concentrates up to 14, 15%. So it's just a function of, hey, we took out a huge volume of gas by removing the CO2. The nitrogen inherently concentrates in that space.
Great. I think we got time. We're at time. We'll just do one more question. What is the lowest LFG flow rate for which a unit can be designed?
Yeah, so we can, you mentioned at the beginning of the presentation, the small digester flow that we had in Brazil, that was 50 normal cubic meters per hour. I don't think you're going to get a 50 normal cubic per meter per hour landfill, but we can scale it down to that level. So there's no bottom limit in my opinion, where the economics could work for membranes, nor is there an upper limit. We've designed one of the largest landfills in the US for this technology as well.
Great. So we are at time. So Greg, I will turn it back over to you for any closing remarks.
Yeah, again, I really appreciate the time and everybody invested in the presentation for as long as they were, and hopefully you were able to get some information out of this. The slides will be presented, so there's a contact if you guys have any further questions, or something pops into your head tomorrow of, oh, let me ask Greg this. Feel free to reach out to that email address, and happy to answer any and all questions and talk to you guys about your specific applications. How can we best serve you? So again, really appreciative to the American Biogas Council for this time today, and looking forward to growing the NRU further. Thank you.
Thank you so much, Greg, for that wonderful presentation. And thanks again to Air Liquide for sponsoring this webinar and supporting the ABC. Also, thank you all for attending. We hope to see you all at our upcoming events like Business of Biogas this October. If you have any questions, you can always reach out to the ABC. Otherwise, have a wonderful rest of your day.